Because I'm an impatient sort, I'm inclined to use an impact driver to start the disassembly. I probably should note here that this drive was delivered with the rear brake rotor removed. This is a brake rotor off a different project, but it is fastened to the final drive with two bolts that go into the crown wheel here, and those are typically originally fixed with some form of Loctite, and it can be a little bit difficult to remove. As in the case of many things, a little judiciously applied heat will facilitate removal. Because this drive is pretty well covered in oil, before I start heating the cover to remove it, I'm going to remove the oil a little bit using some carb cleaner. I tend to use a modest amount of either brake cleaner or carb cleaner as a lazy man's way to degrease things. There's no doubt that breathing this stuff's bad for you, and you probably end up with idiopathic interstitial pulmonary fibrosis if you breathe enough of it, but in the meantime your parts will be clean. This is probably a good time to clean the overall exterior of the drive, just so that when you open it up you're less inclined to introduce junk into the interior of the drive. So we'll blast it with some more harmful vapors here. So we've removed a modest amount of road grime and leaked oil from the exterior of the drive. We can note that this is an early drive when it's off of 2000, as evidenced by the hole for a sensor. What is that? The speedometer sensor, which is not present on later drives, BMW having incorporated the speedo sensor into the ABS sensor on the rear wheel, or at least that's my understanding of it. So now I'm going to proceed to heat the cover, having removed the retainer bolts. I do not have a infrared surface temperature thermometer, so I'm just going to heat it up until it's relatively warm to the touch, and then apply a little judicious force. At this stage of the game, I do not expect to separate the crown wheel bearing from the cover, or the crown wheel itself from the crown wheel bearing. I've just spent 4 or 5 minutes warming the outer cover in the hopes that it will release from the drive housing without too much effort. There's an O-ring on the inside of this outer seal, and the cover simply slides on over the housing. So now let's see what we gain with a little tapping here. These tabs, which serve to hold clips that route hoses for I believe it's the rear brakes and the wires that go to the speedo sensor are probably best not pounded on with reckless abandon. I can see it being possible to actually break those off. However, I do see that I'm gaining by opening up a little crack between the cover and the housing, so I'm going to continue. There we go. So we have effectively freed the cover, and I can tell by the weight of it that the crown wheel and the bearing are still fixed in the cover. So here we have shards of metal from somewhere. This is the taper roller bearing. This typically is not the failure point, and in the limited number of drives that I've looked at, if they haven't been ridden for any extended period of time, this bearing is fine and serviceable and just goes back together again in the assembly. So here's what's referred to the crown wheel. I can tell by turning this there's a fair amount of roughness in how it turns, and there is a good deal of ground up material in here. It looks to be a combination of metal particles and oil seal. So next step is just I'm going to clean up these two parts and then proceed with disassembly of the crown wheel bearing, which is hidden in here, and remove it from the final drive cover. So here are some of the mud that I've removed from the magnet on the final drive oil drain plug, and I can tell by looking at it and having been into this kind of mess before that this at the tip of my screwdriver is a little piece of bearing retainer. If you've read the posts describing failures of these drives, you'll remember that somewhere in the process the bearing retainer fails. The current theory is that the balls and races degrade, putting undue pressure on the retainer, and at that time when the retainer fails, the balls become unevenly distributed, resulting in the seal being torn and the oil coming out and your rear end vibrating and your handling deteriorating. So my next step is to take these components over to my parts washer and just clean them up a bit. So here I am back from the parts washer. My parts washer consists of nothing more than an old stainless steel sink with some kerosene in it and a paintbrush. After slobbering that stuff on the parts, I blow them reasonably dry with compressed air. I am back from the parts washer. My parts washer consists of nothing more than an old stainless steel sink with some kerosene in it and a paintbrush. After slobbering that stuff on the parts, I blow them reasonably dry with compressed air. You'll note that I have done an upgrade of the cleanliness of my towel. My shop rag has gone from extraordinarily dirty to only modestly dirty, and during the process of cleaning and rebuilding the drive, we will incrementally go to cleaner and cleaner until we do the final cleaning prior to final assembly to ensure that we're as meticulous as we can be and not leave behind or introduce any particulate matter that would cause wear inside the drive. The serviceability of the components of the drive housing are to look at the outer race of the tapered roller bearing to make sure that it's free of scoring or notching and that it's smooth and serviceable. Look at the teeth of the bevel gear. Make sure that the surface of the teeth are all free of chips or other defects. and make sure that the bearings of the input shaft and bevel gear are turning smooth and freely without any roughness. I noticed on this drive, and looking at the pivot bearings, that there is notching on these pivot bearing races. So consequently, I would decide to replace these bearings prior to installing this drive on another bike. I should note that somebody posted a while back on the website that they had noticed in the final drives that they had looked at a high incidence of indications of wear on these pivot bearings. So it is apparently a known early wear item. So I've set aside the drive housing, and I'm now going to turn my attention to the final drive cover, which has the crown wheel bearing, crown wheel bearing seal, all still assembled. And I can tell by the feel of it, and you can tell by the sound of it, that the bearing in there is not very healthy. What I'm going to do is clean it off a little bit more so that there's no residual kerosene. I'll probably give it another blast of carb cleaner before I take it into the house and put it into the kitchen oven. There I'll warm it up for about 10 minutes. I probably just wait for the oven to get to temperature around 200 degrees. Then I'll bring the drive back out here and we'll hammer on it and see how easily the bearing comes out of the drive cover. While the final drive cover and the crown wheel bearing and crown wheel are coming up to temperature in the kitchen stove, I spent some time further cleaning the drive housing and inspecting. I basically sprayed it with more carb cleaner, blew it out with more compressed air. Something that is worth noting is that when you remove the final drive from the bike, there will be a universal joint and a shaft which is part of the drive shaft. It is retained on this splined input shaft for the final drive by an internal spring clip. In order to remove that, you want to take a large screwdriver, bigger than the one I'm demonstrating with here, and insert it into the universal joint and give it a good firm pull to get it out. I wouldn't be surprised if these marks here, here, and here are the signs that Sally Boy left as he was trying to extricate that portion of the drive shaft with the universal joint from the final drive. If you are rebuilding your own final drive, there's no need to remove that universal joint and component of drive shaft. However, if you're going to get a swap out, and in the case if this ever goes to somebody who's failed on the road, it will not come with the universal joint, then you will need to remove the universal joint from the final drive on your bike and install it onto this spline shaft on your replacement drive. So here's the cover assembly, hot out of the oven. And I'm going to do a little tapping. It's kind of toasty to the touch here. It was at 200 degrees. And I would not hammer on a new bearing like I am about to, but since this is the old damaged one and I'm trying to get it out of the final drive cover, I'm willing to do a little tapping on it. And there we go. Nice progress. So what we get at this stage of the game, very interesting, Here you get to see first look at Saley Boy's catastrophe. Here's a spring that belonged as an integral component of the seal. The seal has been chewed up, and indeed I found a number of little pieces of seal rubber inside the final drive. Here's the internal aspect of the seal, which is very chewed up. Here are remnants of the bearing cage, and here is the crown wheel bearing. And you can see that there are only 3 balls over here, and then the rest of them are bunched up over here. You could hardly expect that to go round and round in a nice smooth manner. So I'm going to count the bearings on this. I suspect it's a 19 ball bearing, and the original fitment for a year 2000 KLT, but let's confirm that. So I have counted the balls, and it is indeed a 19 ball bearing. My next step, while this is still kind of warm, is to see if I can get the bearing off the crown wheel itself. This is still kind of warm, is to see if I can get the bearing off the crown wheel itself. We should note that the shims that are normally present for the purposes of providing the proper preload, when the cover is bolted to the drive, it puts pressure on the outer race of the crown wheel bearing through the balls to the inner race of the crown wheel bearing against the crown wheel itself, which then loads the tapered roller bearing against its race, which is pressed into the final drive housing. One of the theories, and nobody knows for sure, I guess, as to why these have been failing, is that there may have been improper preload or improper measurement of the shims necessary to provide that preload, resulting in overstress on the crown wheel bearing. I will editorialize here for a minute and say that in many cases, when somebody's looking for one cause of a problem and they list A, B, and C, sometimes the answer is all of the above. If assembly was improper, resulting in spalling of the bearing balls or races, coupled with improper preload, coupled with a slightly inferior bearing, coupled with maybe a design that just wasn't quite beefy enough to take up the slack necessary to compensate for those other shortcomings, put all those things together and you end up with this kind of problem. So that's my theory on it. It's not just one thing. Now, by correcting any one of those, you may minimize the risk of future failure, but I suspect it's probably a combination of those factors. Time talking and fooling around, so I decided to put the crown wheel and crown wheel bearing assembly back in the oven to warm it up a little bit. Here's my bearing removal tool. It's a relatively inexpensive thing from a local auto parts store. Because there's a relatively narrow space between the outer race of the crown wheel bearing and the crown wheel gear flange, I've had to grind on the bench grinder the teeth here of the bearing extractor thinner. If you compare the thickness of this with the other end here, you'll see that I started with something like this and have ground it down to about this. So shortly I'll go to the oven, retrieve the bearing, and see if we can pull those components apart. Rather than purchase this type of tool and wrestle with it, somebody choosing to do a final drive rebuild themselves on a one-time basis might just take the crown wheel and bearing down to their local machine shop and ask them to pull the old bearing off the crown wheel. We're still letting the oven bring the bearing and crown wheel up to temperature, let's hammer away at the seal in the old final drive cover. I usually have a collection of various parts around here, so we'll support the final drive cover with that. Grab any old tool, because we're going to hammer on the deceased bearing seal here and just see if we can't pop it out of there. So there's the final drive cover minus the seal. Here I am back with the crown wheel and crown wheel bearing, what there is left of it, from the oven. I think I'll set it up on my little wooden blocks for additional stability. And let's see if I can get a hold of the outer race of the bearing with the bearing remover. So here I have the bearing removal tool reasonably situated on the bearing. I sort of tap the teeth of the bearing remover in underneath the outer bearing race. Note this is still reasonably warm from the oven. Now the cheater's way to do this is to take the impact wrench, make sure we're in forward, and just see if we can draw that bearing up off the crown wheel, and it seems to be coming, so let's continue on here. And there we go. So we set aside our bearing removal tool until the next time we have to deal with a similar situation. Final drive disassembled, cleaned up, and a new BMW supplied 19-ball crown wheel bearing ready to be installed. My next step will to take this bearing and heat it in the kitchen stove, take the crown wheel and put it in the kitchen freezer and chill it down. That'll take about 10 or 15 minutes, and then I'll bring these two components back out and we should see the two of them drop together very nicely. Okay, so here we are with the crown wheel right out of the freezer, crown wheel bearing right out of the oven. Let's see what we get here. Look at that. So it drops right into place with a nice click. No forces, no bearing press, nothing needed to make it go all the way home. So the stage is now set for me to use Demon's technique for measuring the shim thickness required to establish proper bearing preload. So I'm going to show what I'm going to do here before I actually go through the steps of the actual assembly. We take the crown wheel bearing, place it into its position in the final drive housing. I am then going to take the cover, put it in the oven and warm it up to about 170 degrees. I will then come out, place, without the oil seal in position, place the cover into its normal position and bolt it down using the regular fasteners that hold the cover on the final drive. I will place a couple of small bolts into the location of the fasteners that hold the rear brake rotor onto the crown wheel, and you'll see what we use these for shortly as I progress with the measurement technique. So I'm off to put the cover into the oven, and then I'll be back to secure it in place, set up my micrometer, and then start to measure how much movement there is of the crown wheel inside the assembled final drive housing. Note that under normal circumstances, when the final drive is assembled, the shims are located in this recess right here, and those shims put pressure on the outer race of the crown wheel bearing. But during the assembly for measurement purposes, we will have no shims in there, so that the space that exists between the race of the crown wheel bearing and the seat on the inside of the final drive cover can be measured. So here I am with a final drive cover out of the oven. It was in there at about 170 degrees. I'm going to put just a drop of oil and run it around the inner surface of the bearing seat to try to facilitate movement, and then without too much delay, you see, because the final drive cover is warmed, things kind of drop together very nicely. Fasten these to specified torque, but just snug them down so that we know that the cover is fully seated. And I have my impact driver set at a low pressure setting so I can kind of zip this thing together here. And we'll go to alternate sides of the drive as we take the cover down. So I imagine that's reasonably well seated. Now we'll recover my micrometer. I tried to set this up so that it faces the camera, but you may not be able to see it. My micrometer is from Harbor Freight and costs probably about 15 bucks. My micrometer stand is homebrew, as you can see. It's this magnet from an old speaker, and then just some pieces of metal that I bent. So what I'm going to do, assuming that this bearing is all the way down, and we're going to zero the micrometer, and then just see if we pull the crown wheel and crown wheel bearing up, how much it comes up. You can use any number of tools, and I can see I'm going to want a spacer or a block to work against here. So we grab a couple of pieces of thing, and I'm doing this in such a way as to try to make it visible to the camera, which is altering my approach a little bit. But we just want to get a purchase under one nut and a purchase under the other, and then lift up. And I can feel that whole assembly slid up, and you can perhaps see that the micrometer jumped from 0 to, looks like 16 right now. So what I'm going to do is repeat that a couple of times just to see if it is reasonably repeatable. So I'm going to push it back down again. I felt it go down. Now here it went down, but my micrometer didn't re-zero. It went down to about 3, so I'm going to re-zero it. Note that the drive cover is going to be slowly warming up here, or cooling off rather, and we'll be getting increasing resistance to this little sliding of the bearing. But let's slide it back up again until we get it to stop. And there's my point of resistance. This time I'm looking at 13.5. So I'm going to do this a few times. So here I am repeating the measurement, and I'm going to do this a number of times until I seem to get the same reading every time. So we slip our tools underneath our bolts, pull up until it doesn't seem to want to come anymore, and we see the dial indicator come up to about 13. And we remove our tools and just push down on this. And this time it popped right back to 0. So it's just a fraction away from where I originally set it. So let's do that a few more times and see if we keep getting the same reading on the micrometer when we pull the crown wheel up. Basically moved the crown wheel and crown wheel bearing up and down inside the assembled housing 5 or 6 times and measured the amount of movement and gotten the same measurement each time I did it. So I'm fairly confident that I have an accurate measurement of the amount of space between the outer race of the crown wheel bearing and the seat that is on the inside of the final drive cover. I'm now going to disassemble, remove the cover, and look for appropriate shims, and we'll go through the calculation process here shortly. So the disassembly here is very much the same as the first disassembly. However, all we're doing at this point is removing the cover, and we are not going to remove the bearing from the crown wheel itself. We're just going to remove the cover from the housing. So I have removed the cover from the final drive assembly, and I'm just going to set it aside and move on to calculating shim thickness. Just to review my micrometer measurements, when I had the drive assembled and I was moving the crown wheel with the bearing up and down, I was observing a needle movement which went from 0, having zeroed the micrometer with the crown wheel in the down position, and then raising it up. I was observing repeatedly that the indicator was coming up to about the 13 mark. And on this micrometer, that equates to 0.013 inches of movement. That tells me that the space between the outer race of the crown wheel bearing and the seat on the inside of the final drive cover is 0.013 inches wide without any shim installed. I want to be sure to give D-Man credit for arriving at this technique, which allows measurement of the preload for a final drive without purchasing or fabricating BMW special tools. So we observed using his technique that in this combination of final drive housing and newly installed bearing, that the space is 0.013 inches. Converting to millimeters and rounding, we find that that space is 0.33 millimeters. The BMW service manual specifies that the preload of the crown wheel bearing should be between 0.05 and 1.0 millimeters. So if we add that preload to our observed space, on the low end we have 0.05 plus 33, which comes out to 0.38 millimeters, and on the high end 0.1 plus 0.33, which comes out to 0.43 millimeters. then we can observe that the shims are available in 0.05 millimeter intervals. And if we round my low number up and the high number down, in both cases, we come out with 0.4 millimeters. So the shim that I would use in this final drive would be a 0.40 millimeter shim. Final reassembly of the drive. My previous calculations told me that I wanted 0.4 millimeter shim for preload, and from my inventory of parts I have one. I just so happen to have something that's right at 0.4. So there's our shim. Here we have the final drive crown wheel bearing, new one installed, and in the oven is the final drive cover ready to go on. So we'll go retrieve that and put things together. Final drive cover, toasty warm from the oven, and the shim. So I'm going to place the shim on the crown wheel bearing, and then carefully locate the cover over the shim, making sure that the shim goes into the seat, and lining up our holes. We should be able to just, because the cover is warm, have it drop right down into place. Holes are all lined up, and we can do a quick reassembly So using the impact driver on a very low air pressure setting, just snug the final drive cover down, and then we'll come back with the torque wrench and torque these fasteners specification. After getting all of the fasteners snug down, we just torque them all to specification, and the last thing that remains to be done is installation of the oil seal. I have put a little bit of wheel bearing grease on the lips of the oil seal and on the rotating surface of the crown wheel to facilitate placement of the oil seal, and now all that remains to be done is to just tap it into place.